Let's begin with a presentation. This is mostly a demo class, and we will see a little background about the design and analysis of structures in ETABS, what that involves, what it entails, what does it mean to analyze a structure or design a structure. Mostly a demo class, but also a little bit basics. And this will be our presentation for this demo class. Let me begin with the slide. In this first slide, what will this training course cover? I will deal with this slide at the last. I will be describing what we will be learning during the training course. Our training course will be for 12 to 14 days as per necessity, and we will be learning how to design a residential RCC building based on IS code 1893-2016. I will come to this part of our presentation later. First, what do you mean by seismic resistant design? What do you mean by what is the design philosophy? And there are main 3 points. 3 points in this design. First, number one, under minor but frequent shaking, the main members of the building that carry vertical and horizontal forces should not be damaged. That means when the earthquake shaking is of minor magnitude, when the magnitude is less, the shaking is, but that minor shaking may be frequent. In such conditions, the main members of the building, that means the load-carrying members, should not be damaged. However, the non-load carrying members may sustain little or repairable damage. That is, this is the case of minor shaking. Under moderate but occasional shaking, the main members may sustain repairable damage. In minor shaking, the main members should not have any damage. In moderate shaking, there will be some damage in the main members, but those damages are of very minor nature, they are of repairable nature, while the other parts of the building may be damaged such that they may even have to be replaced after the earthquake. And the third point, under strong but rare shaking, the members may sustain severe damage in both structural as well as non-structural parts of the building, but the building should not collapse. That means, however greater the damage may be in the parts of a building, the building should not collapse. The main purpose for the building not to collapse is because our main objective of design is life safety. We want to save the lives of people. The building may damage, or there may be loss of property in that sense, but it should not collapse so that people are safe and their lives are saved. These three are the design philosophy of any seismic resistant building design. We will be using ETABS software for the design of RCC building in this course. ETABS means Extended Three-Dimensional Analysis of Building System. ETABS is a product of Computers and Structures, Inc. This software is applicable to the analysis and design of multi-story building systems. You may have heard the names of other softwares like the softwares of Bentley, Tekla Structures, or SAP 2000. SAP 2000 is also a product of Computers and Structures Inc. That is CSI software. SAP software is a more general software that can be used for design of bridges or trusses besides building, but ETABS is mainly focused on the design of building system, multi-story building system, and it is a finite element analysis based software. What is finite element analysis? We will come to that in the next slide. I think most of you agree that this is the most used software by structural engineers and architect firms across the world because of its easy to use features. It is very user friendly. The user interface is also very clean and very easy to use. And the latest version is version 19, but we won't be using version 19 during this training course. I am currently using version 18, but you can also use 15, 16 because the interface is the same, the modeling techniques, the workflow that we adopt is the same. There may be some differences in the design results, and that is mainly due to the features included in the software, but that won't be much of a problem. I will be using version 18, but you can use any version whichever you have installed, or we will be providing version 18 software before the start of the training course. So what does it mean to analyze a building, or what does it mean to design a building? Mainly in this training course, we will be learning about first modeling of the building. Modeling means we have a real structure. Building is a real structure which exists in reality. How can we model? That means a building may have different parts. How can we represent those parts when we are designing the building? There will be beams, columns, slab. How do we draw those beams and columns? How do we define their cross-sectional properties or material properties or any other property? Modeling, that means modeling, and after modeling we analyze the model that we have prepared in the software. Analysis means determination of the response of a structure to excitation. In our case, excitation means the earthquake forces, that is the displacements that are generated by the earthquake during the shaking of the ground. In response to those excitations, how does the response react? Sorry, how does the structure react? Reaction response. Real structure is governed by partial differential equations of various order. Direct solution of these mathematical equations is only possible for simple geometry, simple boundary, and simple loading. Complex structure requires simplified methods such as finite element analysis. As I have already told, ETABS is a finite element analysis based software. Analysis leads to the calculation of displacement, strains, stresses, and stress resultants. What are the final results that we get after analyzing the model? We will get the displacements. From those displacements, we can calculate strains. From those strains, by using constitutive relationship, we can calculate stresses. I think we have learned about something about constitutive relationship during our bachelor's course of infinite element analysis, and those stresses are used to calculate stress resultant. In analysis, we calculate these various displacement, strains, and stresses, and in the design part, those displacement, strain, stresses are used. The results of the analysis phase are used as input in the design phase so that the structure can sustain the excitation with an acceptable level of response. We have to define that acceptable level of response. What a response shall be acceptable, how much damage in a building is acceptable, or how much the deflection of any beam or column is acceptable. Those, after defining those acceptable level of responses, the building is designed to sustain that excitation with our defined acceptable level of response. So what is finite element analysis or finite element method? There is a picture here. We can see, let me just, so here is a picture. Let's just see the left side of this picture. You can see something like different grids in the shape of a rectangles on this slab of the building, on the other lower slabs too, and the right side, you might or might not understand, there is perhaps the resultant stresses shown by different colors on the right side of the building. So let's just see this left side. In this left side, there are different grids. This whole one slab is being divided into different elements. So what is the main principle of finite element analysis? It is a discretized solution to a continuum problem. Continuum problem means, what is a continuum structure? The buildings, the beams, the column, the slabs, these are the continuum structure. Continuum structure is a real structure, and we break down that structure, we discretize that structure into different elements, small elements. Like in this slab, it is divided into these rectangular elements, small rectangular elements. So we break a whole continuum element into its various small components. That means we discretize that element. This is the main philosophy of finite element analysis. We analyze the member by breaking down into smaller components. So FEA uses FEM. FEM means finite element method is a numerical procedure for solving partial differential equations. As I have already told, uh, determining the response of a building system is mostly a partial differential equation. Those responses are governed by different partial differential equation which may be quite complex and not readily solvable. So FEM uses a numerical procedure to solve those partial differential equations associated with field problems. Field problems may be displacement or strains with an accuracy acceptable to engineers. The overall process is we first have to prepare the finite element model. As I have talked, the sequence, our workflow will be first modeling, then analysis, and then design. So first we have to prepare the finite element model, and while preparing the finite element model, we have to discretize the structure. We have to break it down into its components. We have to prescribe the loads. The loads shall be is given by different codes, and we will be prescribing those loads upon those elements. We have to prescribe the supports, what sort of supports, what sort of restraints or constraints that we find in this structure. And once the modeling part is complete, now we will perform calculations to solve that problem or to solve those partial differential equations, and this will be done by the software itself. For solving those problems, these differential equations, or performing those calculations, the software generates stiffness matrix for each element. We have learned to find the stiffness matrix during our undergraduate course also, and these individual stiffness matrices are assembled to form the global stiffness matrix, capital K. That means the stiffness matrix for the whole structure. These loads that we assign to the structure are then assembled into the form of a load vector. We impose support conditions, and then this equation will be solved for the displacements. We know this equation: force is equal to stiffness into displacement. This stiffness will be the stiffness matrix, the global stiffness matrix of the whole building. F will be the force vector that we apply on the building, and U will be the displacement vector that we will generate by solving this equation. And this calculation part is only solved by the software itself. So this is the general or overall FEA process. And in this overall FEA process, some part it is the responsibility of the user or the designer. Some part it is the function of the software itself. We don't have to give any input to that. And for some part, some work is done by the software and some work is done by the designer or the user. This is shown in the next slide. This shows whose duty is it, who performs that part in the finite element analysis process, whether it is engineer or software or the combined action of engineer and software. First, evaluation of real structure means what sort of structure do we want to build in reality. We have to evaluate that real structure and then create the structural model. These two components, these two functions is the sole responsibility of the engineer or the designer. We have to create the structural model based on our evaluation of our real structure. After creation of the structural model, we have to discretize the model. As I have already told, discretization means breaking down of a continuous structure into its various components. This discretization of the model requires input from engineer also, while finite element software performs the overall task. Some input is made by the engineer and most of the work is performed by the software, and then that discretized model is solved by the finite element software. This solving part is the lone responsibility of the software. Then we have to interpret those FEA results. Some interpretation is done by the software itself, some interpretation we have to do by ourselves. And what are the significance of those results? That is the responsibility of the engineer to determine the physical significance of those results. Both engineer and software can perform interpretation of FEA results. So there are different seismic analysis procedures. The one that we will be learning in this training course is the equivalent lateral force procedure or the linear static procedure. Sorry. Let's look at the table on this right hand side. Based on our structural model can be linear or non-linear, and our seismic loading can be static or dynamic. Based on these four factors, we have created some sort of a matrix here. So our analysis procedure might be linear static or linear dynamic or non-linear static or non-linear dynamic. Linear static. So what does it mean for a structural model to be linear? You can see here E, A, I, L, G all are constant, K equals to constant. E modulus of elasticity, area of cross section, moment of inertia, length, these all are. Why elastic modulus is the material property that, and this cross sectional area, length, moment of inertia, that is the geometrical property. So both material property and geometrical properties are assumed to be constant in linear analysis. When the structures are subjected to seismic excitations or the vibrations, then we assume that the elastic properties or the geometrical properties or the material properties do not change. That means our structure is linear. Non-linear means these properties do not remain constant during analysis. Seismic loading is static and dynamic. We can either apply dynamic load to the structure. Dynamic loading means their magnitude or direction change with change in time. Static means the force is constant. We derive a constant force and apply to the structure, and we determine the response of the structure. These linear static analysis can be performed by ELF procedure, equivalent lateral force procedure. Linear dynamic, we have two methods, response spectrum analysis. This may not be, response spectrum analysis is not a totally dynamic process. Some part it seems static, some part it seems dynamic. It's some sort of pseudo-dynamic process of analysis, or we can perform linear dynamic analysis by linear response history analysis procedure. In nonlinear static, we have pushover analysis. Pushover analysis is mainly used. This response spectrum analysis, after performing this equivalent lateral force analysis, we can perform the response spectrum analysis also. But this pushover analysis is mainly used to ascertain the strength of an existing structure, not for the design of a new structure, but determination of strength of a current existing structure. And then we have nonlinear dynamic analysis. This can be performed by nonlinear response history analysis. So equivalent lateral force or linear static method is that method which we will adopt during this training course. We will also learn about response spectrum analysis and how to perform it. Perhaps this will be a one class. We can finish this in one class after learning about linear static analysis. So what is equivalent lateral force procedure? As you can see in this slide, building codes specify procedures based on empirical equations, design charts, and other simple rules and limits. We have our own building code of Nepal, that is Nepal National Building Code 105, which has been recently updated and published in 2020. Or before this updated version came out, we have also been using the IS 1893 code. So what is the function of a building code? Building code give us a sort of cookbook type procedure for the design or analysis of a structure. They have their empirical equations, they have design charts, they have formulae, which these all are used for the design of our structure so that we can produce an engineering design without detailed and computationally expensive procedures. That means when we really want to design a structure or perhaps a complex structure, in that case, what we have to do is first we have to determine the hazard level of that site in which our structure is going to be built, and based on that hazard level we have to determine our acceptable response of a structure, and then design and analysis has to be performed in a sequential manner. But for simple structures, we neither have time for performing all those steps, or nor do we want our design process to be that expensive. So in that case, we will follow our building codes, which prescribe certain equations, certain formulas for the design of our structure, so that we can build a structure without having to spend so much of time and money. So equivalent lateral force or equivalent static force is based upon the design principles of a building code. It is a building code specified design procedure. ELF analysis method is commonly used for the seismic analysis and design of ordinary and irregular buildings and structures. What are the limitations of this method? We will be seeing this when we look at the code. The code prescribes the situations in which we can use this analysis technique. For special structures, the code proposes response spectrum analysis procedure. We will also be looking at this design process in this course. So the basic notion of ELF is to convert the seismic excitation, that is, to convert the earthquake forces to an equivalent static force. That equivalent static force, which represents our earthquake scenario, is then applied at the base of the building, which is known as base shear. Then that base shear is distributed to various levels of the building or various parts of the building. So how we will do that, how we will convert that excitation to an equivalent force, how we will apply that force to different parts of the structure, we will learn that in detail when we are designing the structure. Just remember this, the basic notion is to convert a dynamic vibration. This seismic excitation is a dynamic loading. We convert that into an equivalent static force and apply at the base of the building. And we distribute that base shear to different levels or different stories or different parts of the building, and that design seismic force at each level shall be distributed to individual lateral load resisting element through structural analysis considering the floor diaphragm action. First, the force is applied at the base of the structure, base shear, then that is distributed to different parts of the building or different floor level of the building, and from each floor level that force is distributed to individual lateral load resisting element in that particular floor level, and that is done through analysis. That analysis is performed by the software itself, and after that force is distributed to individual elements, based on that force we will perform the design of the building. So this is the general methodology or general principle of the equivalent static force procedure or the linear static procedure. I want to talk little about this basic aspect of seismic design. What we already know, or most of us know, is that we are not designing an earthquake proof structure, but we are designing earthquake resistant structure, because as we saw in the first few slides, a basic seismic design philosophy, when there is a high level of ground shaking, our principle is life safety, that people are not killed, their lives are saved. For that, there may be significant damage to the structure, but the structure should not collapse. That means we are allowing the structure to have its damages, but we are not designing an earthquake proof design. Earthquake proof design might be necessary in some very critical buildings such as nuclear power plants, when because of the nature of the work that is performed in those buildings, we expect them to be earthquake proof. There should not be any vulnerability in the structure, so we basically design them as earthquake proof, but in other structures we do not design an earthquake proof structure. Buildings are designed only for a fraction of the force that they would experience if they were designed to remain elastic during the expected strong ground shaking and thereby permitting damage. Let's look at this structure. Let's look at this graph. In the horizontal axis, we have the lateral deflection of the roof, delta roof, and in the vertical axis, we have the lateral force. Here it is. We are applying lateral force yachts at the roof of the building, and its displacement is given by delta roof. So if we assume the structure to be elastic during the whole period in which the earthquake force is applied, then this graph tends to have this character, straight line character. Is the lateral force is increased, the lateral deflection is increased in a proportionate manner, and this will be the maximum force if the structure remains elastic. But we rarely design a structure for this whole elastic force or this whole maximum force, because that would be a very uneconomical design. We somehow reduce this maximum force by using certain factors, and because we permit the structure to damage, the structure won't be experiencing this maximum force. The lateral force versus lateral deflection curve in actual structure will be somewhat this curved figure, because the structure will be allowed to be damaged after experiencing certain force, and due to this the actual earthquake force that the structure experiences can be reduced. There is a reduction in design force when some damage can be allowed. And here you can see this horizontal line represents the minimum design force the code requires to be used. You can see the difference between the maximum force and the minimum design force. There is a big difference. So buildings are designed only for a fraction of the force that they would experience, because we permit damage in the building. And what is the property of the building that allows it to damage by dissipating the energy without actually collapsing? That is the ductility. Ductility is the property that allows buildings to stably withstand large displacement demand through structural damage without collapse and undue loss of strength. So we will be learning after designing a structure how to make it ductile, how to perform the ductile design of beams and columns, and what codes should we follow for ensuring ductility in the building. If you see the graph in the left hand side, there is lateral force versus displacement. This is another graph. As we can see, if a structure has good ductility, if the structure has medium ductility, and if the structure has poor ductility. The structure has poor ductility. Once this straight portion of the graph ends, there is a collapse of the structure. There is an unexpected loss in strength of the structure, and the structure will collapse without allowing for the effects of ductility to take place. But if we design a structure with good ductility, there won't be a sudden collapse. After yield of the structure, there will be dissipation of the energy, and the structure will remain intact after the structural damage without any unexpected or abrupt loss in strength of the structure. So this is the basic concept in the design of any structure, any seismic design of any structure. That is, we won't be designing the structure for the full force that it may experience during the period of an earthquake, but we will reduce that force by using certain factors. And this is possible because we are allowing damage in the structure. We are not building an earthquake proof structure, but we are only building an earthquake resistant structure. So what is earthquake demand versus earthquake capacity? As we discussed in the previous slide, during an earthquake, certain forces will be applied at the base of the building known as base shear, and our structure has to be designed to withstand that base shear. So that base shear which is applied at the bottom of the building is the earthquake demand. That force is the earthquake demand. Let's see here, deformation demand on the building. The method of design of building should take into account the deformation demand on the building. What forces act on the structure? What is the demand that is imposed on that structure? And the deformation capacity of the building. And then based on that forces, what capacity of the structure shall we give? What capacity shall we give to the structure in response to the demand that is imposed in the structure? because that demand has to be balanced by the capacity of the structure. So earthquake demand on a structure depends on the seismotectonic setting of the location of the building, because if we are in a very earthquake prone zone, or our building is located near fault zones, or the nature of our soil is such that it amplifies the earthquake waves, it amplifies the earthquake forces, then there is a higher demand on the building. The base shear acting on the building will be of higher magnitude. And deformation capacity is within the control of design professionals, although both demand and capacity have inherent uncertainties. Deformation capacity is more within the control of design professionals, because we will be providing that capacity to the building, we will be providing that capacity to the structure based on maybe one example can be we can provide cross-sectional elements such as beams and columns of higher cross-section or a higher modulus of elasticity by using a proper material. So we can impart that capacity to the structure. So that is mostly within the control of design professionals, although in both the demand and capacity there are inherent uncertainties. So if we look at the graph in the right hand side, this is a graph of displacement versus the lateral force. We have already seen this. If we assume the linear behavior of a structure, that is the structure does not yield or does not damage during the earthquake, this point will give the maximum lateral force induced in the building. But if we have designed for ductility of the building, if we assume non-linear behavior of building, that means after a yield point, after occurrence of yield point, the structure gives in, that means it yields to the forces and behaves non-linearly, in which there is dissipation of energy, there is damage in the structure, then this curve will give us the maximum lateral force induced in the building. So in this curve we have taken 3 points. This means low deflection or low displacement, low deformation. For this point there is a medium deformation, and for this point there is high deformation, because as we gradually go along this curve there will be gradual or there will be an increase in the deformation of the building. This is the last slide. So before ending, I would like to return to our first slide and see what we'll be learning in this course. So what will this training course cover? Our training course has a period. We will be conducting the classes 1 hour to 15 minutes per day, and our classes will be for 12 to 14 days as per necessity. If we can go along a fast pace, maybe we will include some more concepts related to design of structure and ETABS. So I haven't fixed the number of days, but it will be 12 to 14. And in this training course, we will learn from the very basic, and along as the course progresses, I hope there are many videos in YouTube or in any other sources from where you can learn the design. But in this course, as we progress along, I will be also giving some theoretical background, some concepts related to why we do this or why we do that while performing the analysis and design of the structure. What happens if we use another option? So there will be ample or theoretical concepts along with learning how to model, analyze, and design the structure. The training course will include entering basic input data. So that starts with setting correct units in our model and choosing the design code based on which code we will be drawing, and drawing the grids. We'll talk about this drawing with grids later when the course actually begins. First, we will be defining the materials for RCC and reinforcement. What grade of concrete will we use, what grade of rebars we'll be using, and then we'll define the frame sections and slab section. This includes defining of beam, column, slab, and in those frame and slab section we will assign material properties that we have defined in the second step, because now frame and slab section will be made of certain materials. We have to assign the properties of those materials to those sections. We will learn about stiffness modifier for frame and slab section, What does our code say about those modifiers? What happens if we use those modifiers? What happens if we don't use those modifiers? We will be defining diaphragms. We will learn about the difference between rigid and flexible diaphragm. When to use a flexible diaphragm, when to use a rigid diaphragm. What will be the difference if we use a rigid diaphragm versus what will happen if we use a flexible diaphragm? So after defining all that is necessary for building the model, we will then actually draw the model. We will then perform the actual modeling of the structure. This will include beams, columns, slab, or mainly these beams, column, and slab. We will draw all that is necessary. Then we will assign diaphragms, restraint, constraint to the structure. We will be learning what are the differences between restraint and constraint. Then we will define the load patterns. That is, after the modeling of the structure is complete, we have seen in our previous slides, we assign the loads to the structure, but before assigning those loads, we have to define those load patterns. What sort of loads will come into our structure? What will be their values? How will they act? So different loads can be dead load, live load, superimposed dead load, earthquake load. We will be learning what is mass source, how to properly define a mass source, and what sort of load should be included in the mass source. You will be learning in detail about mass source. And after defining the load pattern, and there will be load case. We will also talk about load case. What is the difference between load pattern and load case? Then we will define load case and define load combination. We will calculate and assign those various loads. And after this, after the completion of the modeling of our structure, then we will analyze our structure. We will check how can we find if we have done any error while modeling the structure. After analysis of the structure, we will look at its deformed shape. We will see if that deformed shape is allowable in reality. By looking at those deformed shapes, we will check if there is any error in the modeling of our structure. We will see about the displacement, deformation, roof drift, many other things, and we will check the structure. After performing that analysis will be linear static analysis. We will check the structure after its analysis, and finally we will be doing the designing the structure. We will check the design outputs and optimization of a structure. We will see about rebar percentage, what the rebar percentage is acceptable, in which case we have to increase the member sizes, in which case we have to decrease. We will also see about PMM ratio. We will learn about joint strength. There will be 4 or 5 or even 6, 7 checks that have to be performed once a structure is analyzed and designed. We will see about all of that in detail, and then we will design the elements of the structure, including foundation, beam, column, slab. This safe software shall be used for the design of isolated footing. And after all the checks are completed, all this analysis design is completed, then we will look first brief introduction to linear dynamic analysis. This linear dynamic analysis, as I told previously, or the response spectrum analysis, we will look that in a little more detail with respect to those non-linear static or dynamic analysis. We will learn about response spectrum analysis. We will learn about base shear scaling, why we have to perform that. We will learn about how to perform this linear dynamic analysis. And finally, we will discuss on this updated Nepal National Building Code NBC 105, and we will then compare it with this IS 1893 code. What are the differences? What are certain additional things that you have to consider when designing with National Building Code? Because many of us are used to with designing with IS code, and in Nepal National Building Code 105 there are some additional things that we have to take care about, that we have to study. So we will have a discussion on Nepal National Building Code and compare it with IS code. So this is the end of this demo class. I hope this course will be very useful for those who choose to attend it, and we are mainly focusing this for the students who are currently performing their undergraduate course in civil engineering or who are freshers. I assure you that this will be a very good training course. This will be very helpful for learning, and at the end of this course, perhaps this will inspire you to perhaps study on your own about various concepts or learn about these analysis, design, finite element modeling things by your own, even if you are not a if you even if you do not go for a higher study, even if you are not involved in any higher study, perhaps this will inspire you to learn about these various things on your own. So this is the end of this demo class. Let's hope we shall meet again when the course actually begins. Thank you.